All right, let's take a look at how to graph logarithms by hand. So a logarithm is an inverse of an exponential function, meaning if I had something like y equals 2 to the x, I can just take powers of 2 and evaluate that, as opposed to right here where I say the log base 2 of x. When I'm looking at this, what I want is for x to be a power of 2. So 1, 2, 4, 8, etc. How do we graph this? Well, the general process for graphing this is to first consider the inverse of this logarithmic function. So since this is base 2, the inverse will be the exponential with that same base. So that's 2 to the x. Now when I'm doing this, here's the trick. I'm going to need two tables. So I'm going to make one table for x and 2 to the x. And 2 is small enough where I can go -2, -1, 0, 1, and 2. I should be able to get 5 halfway decent points. 2 to the negative second is 1/4. 2 to the negative first is 1/2. 2 to the 0 is 1, and so forth, 2 and 4. All right. So those are the points of y equals 2 to the x. And I'm going to go ahead and plot those right here, although generally speaking you are not going to plot these points. You'll see what I mean as we go through this. 2 and 4. So these points right here, I grab a pen, are y equals 2 to the x. All right. Now, what I want to do is graph the logarithm. Well, the logarithm is the inverse. An inverse switches the x's and y's. So what I'm going to do is make a second table right here for x and the log base 2 of x. Since I'm switching the x's and y's, I'm going to literally do that and switch these two columns. So -2, -1, 0, 1, and 2. And over here I have 1/4, 1/2, 1, 2, and 4. Now what I want to do is I want to plot these points. All right? So 1/4 -2 is down here. 1/2 -1 is about right here. 1, 0. 2, 1. 4, 2. And I could keep going. The next would be 8, 3, which would be just off this grid, so right over here somewhere. And what I want to do is, again, put a curve through these. So that graph right there in green is the logarithm. That is y equals the log base 2 of x. All right? Now, in a normal problem, I may well have some transformations. In this problem, I'm just showing you the comparison between the exponential and logarithmic functions. You see that they are inverses of each other. You might recall two functions are inverses, means they are a reflection of one another in the line y equals x, which is this line with a slope of 1 that passes through the origin. So it's a reflection. Now, it's switching the x's and y's. That's what it's doing. So I can see over here that where this had a horizontal asymptote of y equals 0, when I switch the x's and y's, y equals 0 should become x equals 0, which is a vertical asymptote. Okay? So keep that in mind. And this should make sense too if you think about it as you take, as you plug in smaller and smaller things. Next up out of this would be -3 and 1/8, which will get me a little bit closer. -4 and 1/16. Again, I get a little bit closer to the axis as I go further and further down. All right, let's consider how we analyze these functions. So I'm going to come down here. Hopefully you can still look along with me. But let's consider our domain, range, and so forth. Well, for the exponential function, f of x equals 2 to the x, we know all exponential functions have a domain of all real numbers, or -∞ to infinity. The range was everything above the horizontal asymptote, so 0 to infinity with parentheses. Horizontal asymptote was y equals 0. We had no vertical asymptote, And for end behavior, we knew that on one end I approached the asymptote. So as x went to negative infinity, f of x approached 0. And on the other end, as x approached infinity, I saw this very rapid exponential growth. That's what I see up here. There is exponential growth. This just keeps getting sharper and sharper, and to some extent it might look vertical, although it is definitely not. How about the logarithm? Well, with the logarithm, one of the defining characteristics of a logarithm is what's inside must be greater than 0. So I will have a domain of 0 to infinity, again with parentheses, can't actually equal 0. My domain, my range, well, I can see from my graph that here I get very, very small, and over here I'm increasing pretty slowly, but I do go towards positive infinity. Okay, so this is exponential growth. Exponential growth is very fast, as opposed to logarithmic growth is very slow, but it does continue to grow without bound. All right, horizontal asymptote. Well, the idea is logarithms do not have a horizontal asymptote. They have a vertical asymptote, x equals 0. And you should be noticing here that since I'm switching the x's and y's, what that has done is it has switched the domain and range. The asymptotes are switched up. Similarly, the end behavior will also be switched up. This is going to be a little bit strange, but I can't actually consider what happens as x approaches negative infinity. More on that in just a second. As x approaches positive infinity, what does this function, which is f inverse, what does this function do? Well, if I come up here, I can see, like I said, it's logarithmic growth, which is very slow, but it does keep going very slowly towards infinity. If you think about it, if I wanted this to be 10,000, if I wanted y to be 10,000, well then x needs to be 2 to the 10,000, which is a very large number, which is why the growth is so slow. All right, as x approaches positive infinity, this function, this logarithm, slowly goes towards positive infinity. Well, the other end, and this is sort of mathematically precarious, but x definitely does not go towards negative infinity. The smallest x can get, well, it's bounded by this vertical asymptote. The smallest x can get is really, really close to 0 without ever quite getting there. So I will say as x approaches 0, this function, f inverse, approaches, well, it's falling forever, so it approaches negative infinity. All right? So you want to keep this in mind. You need to understand how to graph both of these functions, and certainly how to find the asymptotes of both of these functions. One of the things, the big thing we talked about for exponentials, the horizontal asymptote comes from the vertical shift. As opposed to logarithms, where the vertical asymptote, because it only has a vertical asymptote, comes from the horizontal shift, or if you will, the 0 of what's inside. So for example, if I gave you a problem where I said y equals the log base 5 of x plus 3 minus 4, I can tell that the vertical asymptote here, I can look at this and say, oh, it's going 3 to the left, or I can just say x plus 3 equals 0, therefore the asymptote is x equals negative 3. So that's the general setup. Now, I want to go ahead and move forward and take a look at how to graph some of these with some transformations. So if you'll follow me to the next page, let's take a look at that. And how we graph these is going to be very similar to how we graphed exponentials. So, here, we're doing log functions with transformations. So, the first thing we need to do is find points from an exponential function. I can see here the base is 3, so I will use 3 to the x. So I'm going to have to make a couple tables here. First off is x and 3 to the x. So with 3, I just go with 3 points, negative 1, 0, and 1. 3 to the negative first is 1/3, 3 to the 0 is 1, 3 to the first is 3. And then I make the table for my logarithm. And that's just going to switch these columns up. All right. Now, just as we did with exponentials, the idea is what I want to plot is the function with everything but the translations, and then I can just translate those points. So I see up here, I want to make a third column where I have vertically stretched by 2. So -1 becomes -2, 0 stays 0, 1 becomes 2. And now I want to plot these points right here. You don't need this middle column anymore. You can scratch it out if you need to. But I want to plot these points. So 1/3 -2 is approximately here. 1, 0 is about here. And 3, 2 is right about here. This is not strictly speaking the parent. The parent would be the log base 3 of x. But these are the points that I'm going to use. I'm going to shift these points to get the graph of my function. So my function, I see x plus 2 and minus 1, which tells me a couple things. 1, the plus 2 is telling me go left 2, minus 1 is down 1. But the other thing I have to make sure I note and include in my graph is that the vertical asymptote is x equals -2. Again, you take that inside, set it to 0, or use that left 2. So I'm going to go ahead and plot that. I'm going to plot this with a marker right here. So here's left 2. Here's my asymptote of x equals -2. Nice vertical line. So I take each of these points. I go left 2, 1, 2, and down 1. About there. I go left 2 and down 1. Left 2 and down 1. And then as best as I can, put a curve through it. And just try and keep that natural feeling to it. It's not going to be perfect, but that's okay. And then I see this function, and then I could analyze this as needed. Again, keep in mind, you got to understand that this is logarithmic. It's a logarithmic function. So it's asymptotic down here. It gets close to that asymptote without ever quite hitting it. And up here, very slow growth. You also need to be aware, if you did try and graph this with a calculator, your calculator is not especially great at graphing things that are nearly vertical. So you'd see on your calculator it would kind of stop around here. So you have to know, 1, how to find the asymptote, and 2, if you're sketching it, to go ahead and draw it all the way down along the asymptote, because it very definitely does not stop. All right, I'm trying to do a couple more here. So next up, I have the log base 6 of x minus 3 minus 2. All right, so again, I'm going to need a couple tables. X and 6 to the x, -1, 0, and 1, powers of 6, I get 1/6, 1, and 6. And then I invert these points to make the logarithm of base 6. So -1, 0, and 1, 1/6, 1, and 6. So I take these points. 1/6, -1, well, 1/6 is relatively close to 0, from a graphing standpoint anyway. 1, 0 is about here, and 6, 1, 3, 4, 5, 6, 1's right about there. So I get this function, and you notice already at this point it looks very flat. But it's definitely not flat. It's just, again, that logarithmic growth is very, very slow. So I can see up here, this is telling me to go 3 to the right and 2 down. It's also telling me my vertical asymptote is x equals 3. So I plot that. It's right there. And for each of these points, I want to go 3 to the right and 2 down. 3 to the right and 2 down. 3 to the right and 2 down. This one, going 3 to the right and 2 down, is going to put me slightly off the grid, but I'll still plot that point to try and give myself a good feel of how to graph this. So right here, it should be close to the asymptote and come up, and you're going to get a fairly sharp curve because of that 6. And I get something like this. And then again, I could analyze that as need be, but you need to remember, this is an asymptote. This is just very slow logarithmic growth. Very slowly, this will go and hit 0 and 10 and 1500 and whatever else I need it to. It does approach positive infinity as x approaches positive infinity. Take a look at one more. So here, I have the negative log base 4 of x plus 1 plus 1. So I'll make a little table right here for the x, negative 1, 0, and 1, 1/4, 1, 4. I'm going to invert these to create the logarithm. Log base 4 of x, 1/4, 1, 4, negative 1, 0, and 1. And I notice right there is a reflection in the x-axis up there, so that'll be my next column, the negative log base 4 of x. So negative 1 becomes 1, 0 stays 0, positive 1 becomes negative 1. And what I'm going to see here is rather than a logarithmic function which is increasing over its whole domain, this one is going to be coming down and be decreasing over its whole domain. So I'm going to plot these points. At 1/4, I need to be up at 1. So that's about here. At 1, I should be at 0. And at 4, I should be at negative 1. So that's right about here. And again, you want to try and put a curve through it as best you can. Remember, there's an asymptote here. Get close, but don't cross it. You can touch it. It looks like it's going to look like it's touching, but it doesn't actually. So that's what we need to understand. So I see the plus 1 and the plus 1, which I know means I go left 1 and up 1, and again means I have a vertical asymptote of x equals negative 1, because I'm going left 1, or because if I set x plus 1 equal to 0 and solve, and I will get x equals negative 1. So I'm going to go ahead and plot this right here, and I get that. And for each point, you want to go left 1 and up 1. So left 1, up 1, left 1, up 1, left 1, up 1, and I can see right there this function has nice y-intercept and x-intercept that I can see plain as day. And again, try as best you can to give it that nearly vertical look during as it gets close to the asymptote, and then that nice sharp curve right there. All right, so that's what it looks like if we reflect. Another note, for reasons that we will discuss in the future, I would get a very similar looking graph. In fact, I would get exactly the same graph if I had a log with a base of 1/4, x plus 1 plus 1. So just note that if your base is between 0 and 1, it will have this same type of behavior where close to the asymptote you're very high up, and for increasing values of x you go further and further down. Again, slowly, but definitely towards negative infinity. Hopefully this has helped.